Okay, hopefully everybody has joined us now, and welcome to the ASEG Webinar series hosted by the ASEG branch. Today we have Rod Paterson talking to us about the application of 2.5D AEM inversion to resource exploration with reference to open file survey examples from New South Wales, Queensland and Western Australia. Before we get underway, I've just got a little bit of background material. Thank you very much to our corporate members, HiSeis, Total Seismic, VelSeis, Southern Geoscience and Santos. Without them, these webinars couldn't be possible. On the state branch side, we've got branch sponsors for South Australia, WA, New South Wales, and we'd really love a branch sponsor for ACT. So please come forward and talk to Marina Costello at some stage. That would be much appreciated. Okay, during the presentation, we can take questions, but those questions will be answered at the end. And ideally, despite what this slide shows you, please put your questions into the chat box rather than Q&A. But it's the same process, so use the chat box and we will try and get to some of those questions at the end. Okay, just to let you know, upcoming webinars on Thursday, 1st of October, we have Ankita Singh talking about grayscale representative elementary volumes, an innovative approach to investigative pore scale REVs from raw micro CT images. Okay, so put that into your calendar and please register as soon as you can. Likewise, a little bit of advertising here for ASEG. You all know about exploration geophysics, preview, reduced entry to AEGC conferences, free entry to regular technical events, etc., etc. Lots of goodies there, well worth being a member of the ASEG. And also, this is a super important reminder too, that remember that you need to get your short abstract submissions in for the AEGC next year with a deadline of 30th of October 2020. Okay. And keep in touch. You can reach out to the ASEG through the email newsletters, through Facebook, through Twitter, through LinkedIn, YouTube. We are on all those platforms. Let's talk to you soon. Okay, before I hand over to Rod, Rod graduated from the University of New England with a BSc in geology and geophysics. Since then, he's worked for a number of government agencies, consulting groups, and has held various senior positions within Cyprus Minerals, Aberfoyle Resources, and also BHP. From 2007, he worked as a senior consulting geoscientist for Intrepid Geophysics, where he has focused his attention on AEM software development and particularly 2.5D inversion. When he's not talking to Jovan Silic about everything airborne EM, you'll find Rod playing guitar or playing competitive tennis. However, that's somewhat difficult in Victoria at the moment, where he's forced to hit balls against a wall, but hopefully that will be over soon. So without further ado, I'll hand over to Rod to take you through the application of 2.5D AEM inversion to resource exploration. Thank you, Rod.
Welcome everyone. Thank you for attending this webinar. This is about the application of 2.5D airborne EM inversion to resource exploration. So an outline, general discussion on 2.5D versus CDIs, 1D and 3D inversions. Discuss cases and environments where the advantages of 2.5D are realised. Demonstrate with examples. Review recent Cobar inversion results and possible mineralised targets with reference to known prospects. Compare CDIs and 1D inversions with 2.5D for these targets. Discuss target uncertainty, misfits, system and geological noise, topography, clearance, IP and SPM effects, and we'll look at some decay curves. So the part one. 2.5D versus CDI, 1D and 3D. So an outline, briefly describe the 2.5D and 1D AEM inversion methods. Highlight the differences between 1D and 2.5D and the geology Geological consequences. The products from each inversion technique vary, with each having its own strengths and weaknesses. AEM conductivity sections are best used when combined with other geophysical techniques such as geochemistry and geology. So what's the primary objective of running an airborne EM inversion? We want to predict the most accurate geological section possible, and we want to find an ore deposit. So why 2.5D inversion? 1D assumes that the Earth can be modelled using a series of horizontal layers beneath each data point. 1D can create artefacts due to topography, tipping conductors, contacts, faults, and sharp electrical discontinuities. 2.5D is accurate for geology, which is reasonably 2D within the airborne EM system footprint, and assumes the geological strike is perpendicular to the flight direction. 2.5D requires less computational resources than 3D and is an overdetermined problem. 3D is invariably an underdetermined problem with more unknowns at data points. So why 1D inversion? 1D forward model is relatively easy to implement as a fast forward solution. Inversion process is easier to manage compared to 2.5D and 3D. It's expected to be accurate over relatively 1D geology, but can produce artifacts and create conductive features over non-1D sections, but it's generally better than CDIs. Capable of inverting data at a survey scale much faster than 2.5D, requires far less computing power. So the differences between 1D and 2.5D. 1D solutions are analytical and fast. So at each station, a vertical column is inverted from the observed multi-channel EM signal. Starting models a series of flat layers with arbitrary starting resistivities increasing with depth. The layered model inversion result is constrained laterally to produce a smooth section. The 2.5D solutions are numerical. A finite element mesh is built for an entire flight line, and then each element in the mesh is solved for using the EM data over a long line distance of 1,500 metres. The starting point's usually a constant resistivity half space. So 2.5D uses the finite element method and uses a full set of Maxwell's equations. Note, analytical is exact, numerical is approximate. So the finite element mesh. So the important thing here is that the elements can be warped so we can accurately model rough topography. So forward modelling a conductive cube within a homogeneous half space, this is a 1D forward model of the cube, and this is a 2.5D forward model of the cube. These are both Z components. So you can see the responses are very different. To estimate a true 1D inversion misfit, we need to model the section response with 2.5D or 3D modelling software, as the following slides will illustrate. So note, this is not 1D, this is definitely 3D. So we're evaluating 1D inversion results by 2.5D forward modelling of the 1D conductivity section, and we see poor agreement between the modelled and the survey data. So the 2.5D forward response is in black, the measured VTEM is in colours, and this is the 1D inversion log conductivity section at the bottom here. And you can see here the colours in the black don't fit very well at all. And the same thing for the X component. Very poor fits. So 1D misfits are poor for Z and very poor for X. Now we're going to look at a 2.5D inversion section modelled response and look to see the difference. So you can see that if we invert this with 2.5D, we get a very good fit between the observed and the predicted data. Colours and the black lines again. And if we do it for the X component, it's not quite as good, but it's still much better than 1D. Another question, should the inversion process use both the X and Z components? We're going to have a look at the Briar Basin, a small area near DeGrussa, and we see the published geological map. It has a shale horizon here which is folded into a syncline. We're showing here the apparent conductivity solutions for these three flight lines. So the conductive body sits in here. So this is the 2.5D inversion response using the Z component only. This is the 2.5D inversion using the X component only. And this is the 2.5D inversion using both X and Z components. So you can see that the shale horizon, the syncline thing, is much better defined by using both components. At least this is true for the towed bird systems, the spectrum survey here. So the joint inversion of X and Z components gives a more constrained solution. Topography. We want to look at some 1D inversion artifacts due to topography. So these are two horizontal sections, and the top one is an SD differential transform, or a 1D CDI, and the bottom one is the GALEI 1D inversion. And we're inverting a 1,000 nanometer half space. The sections show 1D inversion responses due to topography alone. So you can see that generally conductivity is lower over the peaks and higher in the valleys. This is another synthetic model, a horizontal confined conductor. These are the digital terrain contours, and this is the outline of the conductor, the horizontal conductor, and we show the cross section here. This is the topographic profile and the conductor. In the top panel here, we've got the dB, dt, Z profiles for a 1,000 nanometer host rock. It's the half space response, and here is the half space response with the conductor present. So this is the inversion of those responses. So this is the inversion without the horizontal conductor, and this is the 1D inversion with the horizontal conductor. So here you can see that the prediction is actually deeper than the actual model, and we have these very strong pants legs on the edges dipping away. And we can see that the results at the surface and at depth are impacted up to 1 kilometer away. A second model, the vertical thick confined conductor. Again, the digital terrain, position of the conductor, the cross section with the topography and the vertical conductor, and the same, the half space response and the half space response with the conductor present. And the 1D inversion results, the same half space here without the vertical conductor, and then the 1D inversion with the vertical conductor. And you can see we get this anticlinal shape response. The thick vertical conductor is mapped with better conductivity contrast. The depth to the top's overestimated, and the conductivity signature seems to indicate a slight dip to the north. So this is asymmetric here, tending to suggest this is dipping that way, and that's caused by this topographic feature here. Here's a more complex synthetic model published by UBC and presented at AEM 2018. So it's a 3D ring and a folded conductor beneath topography. This is the folded conductor here, the brown, and this is the ring conductor. So you can see in 1D, there's also two resistive cubes here in the model. So in 1D, the response puts a resistive hole in here. In 3D, it's a bit smooth, but it pretty much gets the right answer. For the ring, the 1D puts a resistive hole in the middle of the ring, and in 3D it looks reasonable, though quite smooth. This is a real example from Peace River, Alberta. So in the 1D inversion, we see this resistive artifact at the topographic edge, just in here. And in the 2.5D inversion, you don't see that, and you see much better definition of the thin layer, and also particularly of the second conductive layer here. Much better defined than in here, although you can see that it's there. So 2.5D shows big improvement in steep topography and greatly improves the definition of a second deeper conductive layer. Now we want to visit sharp electrical discontinuities. So this is an example from the MacArthur Basin, Corimbarini. So this is the VTEM line 104400. This is the Z component. And if we look at this, we can see the thing that we're looking at here is a small inflection at late time, which is an off-end effect from a large conductor to the east. Now, if we look at the main points of difference between the 1D, 2.5D and 3D inversions, we see that there's a response to the late time inflection in the 1D inversion, which doesn't occur in 2.5D and is not really there in 3D either, in this position here. Now we're going to do a synthetic model to demonstrate the effect. So this is just the same kind of resistivity contrast, a very conductive slab here against a fairly resistive background. And this is the Z component response, and you can see this little off-end effect here, this late time bump. And there's also a feature in the X component. So a 1D inversion of the 2.5D synthetic model data shows this bump here. And you can see the inversion produces this off-end effect here. So the conclusion is the 1D inversion of the 2.5D synthetic model creates a false conductor dipping steeply away from the edge of the conductive slab. Now, dipping conductors, contacts and folds. So dipping conductors, once the dip of a conductor exceeds around 30 degrees, 1D will struggle to resolve the correct dip. And contacts and folds, in final folds with steep limbs often appear as anticlines and CDIs and 1D inversions. It's the pants leg problem. So here's some examples of different inversion methods. This is from a paper by Lee Cooper, 2014. So this is a 3D inversion, this is a 2D empirical inversion, and these are all 1D inversions. So the three features of interest here are this deep feature, shown in here, the blue, this blob in the middle, this one, and the shallow feature here, which is pretty much correctly inverted for in all of these, simply because it's 1D. So if we look at our inversion instead of the other 2D inversion, we see that the 2D inversion and the 3D inversion don't see this deep feature. The actual flood-lying features are well defined in all of these inversions, well defined in the 2.5D as well. This deep feature in 3D is also seen in the 2.5D, and it's there in the 1Ds, but it's destroyed by these pants leg effects, which are also here and also in here. Now this deep conductor is a little different. So it appears in 3D, not in 2.5D, and also it appears in all of the 1D inversions. Now we're going to look at this in the next few slides. We believe this is actually an SPM effect. So this is just the 2.5D inversion in more detail, showing the misfits and the section in more detail. And now we're going to look at IP and SPM effects. So if we look at this same section again, so we're looking here at this little late time feature. And here it is blowing up. So this little bump here, that is the bump that is being responded to in the 1D inversion here. Now, if we look at the decay curve for this, we see that it has a very flat slope, 1/T, which is an SPM slope. And we can also see, if we look over here, we can see this is a more typical decay curve, an inductive response here. So the valence conductor appears to be an SPM effect and doesn't get fitted by the 2.5D inversion. So part 2, we're going to look at some case studies from Queensland and WA. So environments where the advantages of 2.5D are realised. So this is an example from the East Isa V10 Plus survey in Queensland, and it's from around Dougal River. So 2.5D inversions performed on 8 lines over an 8 by 15 kilometre block. Some of these anomalies have close spatial relationship to the shale-hosted lead zinc mineralisation at Dougal River, and this demonstrates the ability of 2.5D inversion to reliably image steeply dipping and folded geology and present exploration targets ready for testing. So this is the Google Earth location map here. This is the Dougal River mine area. This is some drilling in the red, a few drill holes out here, but we don't have the results of those, unfortunately. These white things here are the shale horizon, which is folded around through here, around this quartzite core. Same thing shown in the geology, the synclinal features. And the same thing appears in the radiometrics image on the right. So these are the two lines we're going to look at, this blue line here and this one here. Now these are the inversion results. So we're comparing the CDI and 2.5D inversions over these two lines. So the 2.5D inversion shows this synclinal slate horizon, and the CDI tends to show an anticline with pants legs and things, complicated response. Over here, there's a response in the CDI, which is thought to be caused by an IP artifact. We'll talk about that later on in the next couple of slides. On the second line, we see both sides of the quartzite have this folded shale horizon, slightly more complicated. But again, the CDI sees this as an anticline, and yeah, these are just the pants leg things. More detailed picture of the geology showing the shale horizon going around through here. So the 2.5D inversion results highlight the synclinally folded slate package. So we've got the red, the synclines, and the grey magenta colours. They're the host to the Dougal River deposits sitting just in here. They wrap around the Napdale quartzite core, which is pale green, yellow, or red in the radiometric image. So this is just the way we look at it in our 2.5D inversion software, showing the misfits, the noise model. There's very little signal in here, so this is below noise level mostly in here. And the two synclinal slate horizons, etc. And now we want to look at the IP effect that we talked about. So So there's a joint inductive and IP inversion that's been developed for the 2.5D inversion software, and the results from VTEM line 15701 are shown below. So this is the normal inversion, just the 2.5D standard Z component inversion. And you can see here, we're not fitting this. And these are IP effects, these negative features here. And if we look across here, this is the joint inversion. This is our noise map. Now, our noise map highlights the IP effects in red. So these IP transients have been fitted in here. And so we're producing a chargeability section as well as a conductivity, log conductivity section. You can see the results slightly different once you take account of the IP. This is just a 3D perspective view of the 8 lines showing the synclinal features on all of these lines. And over in here, unfortunately, we don't see it in here where it's not been flown over the Dougal River mine. So the conclusions, VTEM Plus survey near Dougal River. Although the survey is conducted at a 2-kilometre line spacing, conductivity imaging by the 2.5D software demonstrates an ability to correctly identify the geometry dips of these structurally complex exploration targets. So we're going to have a look at a more iron ore related survey. So the Brockman and Hardy synclinal structures have attracted a lot of exploration and mining development in the last 10 years. And gravity mag and radiometrics have been used as exploration tools. Search for BIFs for a long time. We're focusing on the emerging use of AEM and the role of this technology in optimizing costs and the time taken to define iron ore resources and their physical properties. So in 2014, 30,000 line kilometre Capricorn Tempest survey was flown as part of the West Australian Exploration Incentive Scheme. So we're going to examine 2 lines from that survey that cross part of the Hardy syncline and illustrate how conductivity relates to the geology and the open file mag and radiometrics. This is the Mount Bruce 250,000 scale geology map. And that's the, this is the Brockman syncline, and that's the Hardy syncline at the south, down the south here. And these are the airborne EM Tempest survey lines. And this is a cross section across the Hardy syncline on the published geology map. You can see a well-defined syncline with some fault offsets and things. This is the aeromagnetics. This is a reduced dipole TMI drape on the 1VD. So again, we can see clearly the 2 synclinal features. And these are the Tempest EM line segments. And these are the 2 lines that we're going to look at in detail. So this is the radiometric image, potassium, thorium, uranium 3-band RGB draped on the reduced dipole TMI 1VD. So again, very clearly defined. And in this case, magnetic units are high in KUTH, they're in white. The mafic and iron-rich units high in thorium in green. The non-magnetic felsic units with high K in red. And some magnetic iron-rich units low in radio elements in dark purple and green. This is the Hardy syncline in Google Earth, and these are the 2 lines that we're going to look at across this syncline here. So this is the first line, and this is the CDI, that's the 1D, and this is the 2.5D. And the Hardy syncline sits in here. And you can see here, this is the conductor here is the McRae Shale, and the resistive feature here is the Brockman Iron Formation. This is the syncline in the geological map section. So you can see that it's very hard to see this synclinal feature in the CDA and 1D inversions, but it's quite well defined in here. It's a complex shape here. Some structural deformation. This is the second line, and it's quite similar to the CDA 1D, 2.5D, and the Hardy syncline in here. So again, you see the synclinal shape over the fold nose, and the McRae Shale, the conductor, and the Brockman Formation. And there's also a resistive dolerite in here. So now we want to move on, and we want to look at some Cobar airborne EM inversion results and assess some targets that were selected from the 1D and CDI sections. So this is a regional excite survey with a line spacing of 2 to 4 kilometres. None of the non-deposits have been flown over because of cultural problems. We want to compare 1D and CDI inversions with 2.5D for some of the targets that have been picked. We discussed the assessment of target uncertainty, inversion misfit, system and geological noise, topography, clearance, IP and SPM effects, and decay curves. So this is an overview of the Cobar region. So this is the Cenozoic geology and the airborne EM survey boundary on the left. So this is the airborne EM survey in the blue here. And on the right is the seamless bedrock geology map and the airborne EM survey lines in blue. And we have the non-major lead, zinc, copper, gold deposits here, the Endeavour, CSA, the Peak, Era. And the source of these maps is from MinView, the Geological Survey of New South Wales. So what is our target evaluation methodology? So the survey region, character, and the known deposit properties. So there's a very well-developed deep regolith up to 150 metres of oxidation. The known deposits have a pyrrhotite association and are often magnetic and can be highly conductive in parts such as the Allura Endeavour deposit. So the suggested target evaluation sequence is to pick an anomaly on the section. Make sure you're using a vertical exaggeration of 1 so you can see the correct dips. Check for cultural interference, check profiles for sensible geometry and misfit. If an anomaly is not supported in profiles, then check the anomaly decay curves for IP or SPM and check for correlation with magnetics, TMI, TMI1VD. So another overview of the region. This time we're looking at the mag, and we've got the Endeavour CSA Peak and Hera deposits on here. At this go, you can't really see anything much, it's much too coarse. So these lines were flown at between 2 and 4 kilometres apart. So on the right side here, we have an airborne EM 2.5D inversion depth slice, log conductivity at 172 metres below the surface. So we should be well below the actual overburden effects. And this is some culture. This is a gas pipeline, and these blue lines here are major power lines. So we look at the 2.5D log conductivity depth slices at 26, 120 and 292 metres. And you can see that the shallow one here is impacted by the conductive cover. It's very deep conductive cover in this northern part of the belt, and also down the south here around next to Gibson Vale. So at 120 metres, we should be just getting through the cover, and you can start to see some geological character in here. And at 292 metres, we still have some visible conductive features from the bedrock. But at this scale, you can't see anything that's useful from a deposit picking point of view because of the line spacing. These are the same depth slices from the 1D inversion. You can see that the shallow 25 metre one is quite similar, very conductive at the surface and also down around here. At 112 metres, it's starting to see through, and you see some of the broad features, but there's a bit more contrast between the previous one and this one. You can see, but they have roughly the same features. But at 280 metres, the 1D inversion loses all its character. So the targets we want to look at are picked from this review sequence here from south to north. So we're not going to look at all of them, but we look at Woolshed, Achilles, Cobar, Mount Solar, Scorpio, and Whirlong, and Cobar, these two Cobar ones here. So the first one, the Woolshed anomaly. So we have a conductive feature in the 1D inversion here. And we look at it in our 2.5D, and we don't fit this at all. So we're looking at the decays again. So this appears to be an SPM effect. So if you look at the decay, we see something similar. We see this very flat response here, which is a typical SPM decay. So our 2.5D inversion just doesn't fit that using the default set of Maxwell's equations, but 1D often will pick something from the SPM effect. So you can see here there's also a mag low associated with it. So there's no early time response, and the cover is very thin. So you don't see anything at early time. So that's typical for an SPM effect. Achilles. So again here we're looking at this area in here. And if we look at this, and this is the CDI inversion. In this area, the CDI and 1D inversions are very similar throughout this Cobar. So in some cases we've looked at 1D, in some cases we've looked at both. In this case, we're just looking at the CDI. So you can see here in the 2.5D, there's no response. And we're on the shoulder of an early time feature, but there's nothing in late time. So it looks as though this feature may have something to do with a bust in the actual conductive cover here, causing some kind of pants-leggy effect around this thing. Also here you can see this artifact beneath this resistive hill. There is a conductive feature over here which may be of more interest, but there's no TMI associated with it. Okay, so we're looking at this feature here, not supported in 2.5D. So the Wawara fault, so there's a fault up through here which has these deep conductors apparently associated with it in the 1D inversions. If we look at this in 2.5D, we don't really see anything. No features correlate with the fault position, and there's no deep conductors as there are in 1D. And these inversions have reasonable continuity from section to section. So we're going to look at one in a bit more detail. So we're looking at the southern one, line 10380, and the fault position is at the western edge of a deep irregular feature in the 2.5D inversions. So it's possible that we're getting some kind of off-end effect here, which is causing this feature at depth. Something similar to what we saw earlier with that synthetic example we were looking at. So another line, 10390, the next one over, there's something similar. Again, you don't see anything at late time, so it's hard to imagine what's causing this very deep feature here. Mount Solar. So this is Mount Solar here. So we're looking at this shadowy feature in here. And there's supposed to be some anticlinal domes with arenite cores here. Now, if we look at this, we see this is the actual anomaly here, but we see very little in 2.5D in here, and there's actually no significant feature in the late time to explain this, but there is some shallow conductive features which may have something to do with this. There's actually a magnetic feature here. Also, we have a resistive artifact here beneath this hill. So this is the Mount Solar hill here. And there's an artifact below the resistive hill in the 1D and CDI inversions. So the Great Central South Regina Volcanics. This is kind of similar. So this is the feature in here that we've been looking at. And in here you can see that the conductive cover it's got some sharp edges on it, and particularly over here and in here. And you can see that these features seem to be associated with these breaks in the conductive cover. So there's no discrete dip conductor in 2.5D. There's another artifact below a resistive hill. You can see this thing in here, which seems to be caused by this hill feature. Mount Allen, so this area in here. Now you can see here that the 2.5D doesn't fit this very well. So we're looking at this, and there's obviously some IP here. So we've looked at a K curve in here to just check this, and we can see that this misfit's impacted by IP at late time. This is a typical pull-down effect in the decay curve. So this is an example, just an example of an IP effect that may be having some impact on the 1D inversion. Now the Wagga Tank, Southern Knights Peel. So there's a strong conductive feature here in the 1D. And if we look at this, so this is the 2.5D, we don't see anything. So again, this is very similar. It's hard to explain this based on the profile data. So the only thing that we can say here is this artifact occurs close to a 45-degree turn in the flight path, a 20-metre change in loop clearance, and a 15-degree pitch change loop front edge up. So maybe this has something to do with the sudden change of direction of the flight path of the helicopter. and the fact that it's caused some big changes in the loop clearance and the pitch. Whirl on. So this is a chalcopyrite peritite sphalerite thing, and this feature is almost certainly an off-end effect. We see here the strong conductor and shallow conductor, a slab in 2.5D, and in the 1D inversion we see this sort of artifact at the off-end position. Cobar, main load. So there's a hot layer, flat layer hotspot in 1D and CDI here. But the 2.5D inversion sees a conductive feature, and it's in this inflection here on the slope here. See there's a bit of a bump there. So the profile support's subtle, but the fits are reasonable. So you can see here this looks a bit like a part of a shallow west dipping limb or a synclinal feature. And if we look at the TMI, it's sort of got the same kind of sloping away feature as though something may be dipping in that direction, flat dipping. But apart from that, yeah, it's quite different to the 1D solution. So Cobar Ops, the Curie prospect. It's a more complex response here. So again, this feature in the 1D looks like an off-end effect, but there is some magnetic activity in here, so you probably can't write this off completely. But in the 2.5D, you see a possible conductive feature in here, pretty blurry, which is related to this shoulder at late time here. So just what we've said here. So there's some drilling in there that should be checked for confirmation of regolith depth in that area. So some summary and conclusions. The CDI or 1D inversions are well-established processing strategies for AEM. Experienced users have learned how to recognize the shortcomings of these inversions and are reluctant to change this practice. However, CDIs or 1D inversions can mislead geologists or less experienced users, and as a consequence may result in poor exploration outcomes. So the 2.5D AEM inversion technology developed by Jovan Silic for Intrepid produces very clean and spatially accurate images of subsurface conductivity in both cross-section and plane. The 2.5D inversion products are mostly free of the artifacts often seen in CDI and 1D inversions, particularly where 1D assumptions are not met. We have shown here real examples of the artifacts common to CDI and 1D inversions, which often relate to topographic effects, sharp electrical discontinuities, dipping conductors, contacts and folds, and cases of mistaken identity due to IP and SPM effects. So one of the biggest problems that all types of airborne inversions struggle with is interference from IP effects. This is particularly true for the modern helicopter suspended loop systems, but not necessarily the towed bird systems. The interference is magnified by the high powered and lower frequency transmitter waveforms designed for deeper detection limits. Intrepid can currently jointly invert for inductive and IP responses and is currently working on improving this further using better automatic recognition techniques during the inversion process. Okay. That's it. Thank you. Thank you for your attention.
Yes, thank you very much, Rod. Some fantastic case studies there, and certainly some definitive examples of the benefits of 2.5D inversion over 1D. We do have a couple of questions, but before I go to that, I'll just mention to everybody that this presentation will be available in a couple of days on YouTube, including full presentation sized slides. I'm sorry about that issue there. But look, I'll first go to Mike Aston's question here, Rod. What is the processing time required for 2.5D inversion compared with 1D inversion?
The 2.5D inversion, we can process something like 2,000 line kilometres in a week. And that's using 7 or 8 desktop computers.
Okay, so I guess the other part of his question here was, can it be done on a normal desktop computer power? And it sounds like it can. Yeah.
Yes, it can be. Yeah. So we're using, I didn't go into it, but we're using MPI parallelization to speed things up. And we also segment the inversion into smaller parts so that to limit the memory requirements so that it runs quite easily on a computer with 16 to 32 gigabytes of memory.
Okay, do we have any other questions there from the participants? I've got another question for you, Rod. SPM effect. Do we understand that well enough that we could predict it from outcrop or downhole logs, etc., etc.?
You could do it by looking at the surface to see. Normally, it's a surface effect, and it's usually caused by very fine-grained magnetite in the soil or in the regolith. But there are some examples from very magnetite-rich terrains where the magnetite's fine-grained in the host rock. So, yeah, it's actually quite difficult to pick up. So, if you've flown the AEM, the best way is to look at the decay curves. But in some cases, if you have a mixed response, it can be quite difficult.
Okay, thank you. I've got another question here, again from Michael Aston. What is the comparable processing time for 2,000 kilometres on 1D inversion?
Well, we don't do many 1D inversions, so it's a little difficult for me to say, but it's, I mean, it could be only a day. I'd say you could probably do that in a day. Using the same computing power that we have for our 2.5D, get it done in a day. So we're talking about an order of magnitude difference in time. But it's all got to do with your compute resources, how quickly you can get these jobs done. Obviously, there's an investment in computing resources that has to be considered. We're trying to do a cost comparison.
Okay, and a question from Tim Monday. One of the challenges in 2D and 3D inversions is defining the initial grid discretization. What is your workflow for setting that in an unknown geological environment?
What we do is we look through the, first of all, we can use more than one resolution in our inversion. So we look through the profile data and we look to see if there's any narrow, deeper conductive features that we need to take care of. So then we segment the inversion into high resolution and low resolution. So we use maybe a 20-meter cell resolution for areas where we think we need to be sure that we can, properly fit something that's quite narrow. And then, so we go through and just select those areas. It's not done automatically, so you have to make it trip through your profile data, but we have a very fast way of doing it interactively in our GUI. Does that answer the, is there any follow-up to that? So yes, we can invert parts of the the line at 20 metres and the rest at 40 metres is normally what we do if we have that situation. Assuming that the helicopter's up about, the loop's up at about 40 metres, and going finer than 20 metres doesn't make a lot of sense. 20 metres seems to be a good optimum for high resolution thin bodies.
Okay, and look, just one more from Houston. I don't know whether you can see it there on the chat box on the right-hand side.
I can't see that. I might have to close my presentation, do I?
But there's actually quite a few questions here, but I guess lastly, IP doesn't behave like individual spikes as shown on section. Can you explain?
No, it doesn't behave like that. It's usually, did I show something? I'll go back to the slide. Just hang on a sec. This is the IP that I was talking about. It's not a spike or anything like that. It's usually flat-lying layers near the surface, commonly clays, but there are other kinds of IP that are associated with dipping units and things that have been shown in recent studies. So does that answer the question? No, they're not spikes. They're quite broad features because they tend to be horizontal layers, nearly horizontal, in most of the cases that we see. A lot of the IP contamination is coming from the regular, in all the surveys that we've had experience with.
Okay, actually, Houston, back to you. Do you want Rod to elaborate, or you're happy? Okay, well, look, thank you very much, and a big virtual applause for Rod. That's a fantastic fly through 2.5D inversion and some great case studies, as I mentioned before. Don't forget the talk coming up in October, and thank you very much for all your participation. Thank you.
Thank you, everybody.